Hello everyone, I am Jia-Ruei from Robotics Systems Lab at ETH Zurich. Today I'm presenting to you our collision-free MPC for whole-body dynamic locomotion and manipulation. When it comes to mobile manipulation, it is essential to avoid self-collision and environment collision during manipulation and locomotion. Compared to a wheel-based robot, the floating base of a leg manipulator provides more degrees of freedom, but also increases the system complexity. Instead of saving computational time with this conservative collision avoidance strategy that may sacrifice the range of motions, efficient whole-body coordination between the arm and the body is necessary to take full advantage of the floating base. Therefore, we propose a collision-free whole-body framework capable of real-time coordination between locomotion and manipulation with self-collision and environment collision avoidance. Our framework is composed of a whole-body MPC planner implemented by the OCS2 toolbox and a whole-body controller solved as a hierarchical quadratic problem. By simply providing the robot URDF with collision primitives, both self-collision and environment collision distances can be computed. The cost function of the MPC planner is then augmented with all penalties on the collision distances. The sole dependency on the robot's URDF makes it easy for our framework to generalize over various systems. For self-collision avoidance, the distances between collision primitives are computed using the FCL library with the forward kinematics updated by the Pinocchio library. For our quadrupedal manipulator, we consider the distances between the two collision bodies on the arm and 3 on the body. To avoid obstacles in the environment, the collision primitives are automatically approximated with a set of collision spheres, and the environment point cloud is mapped to a Euclidean side distance field using the Fiesta algorithm. With these two components, the approximate distance from the robots to the environment can be simply queried at each sphere center from the Euclidean side distance field. Together with the fast updates of the Fiesta algorithm, this strategy allows us to avoid both static and dynamic obstacles. We normalize the average MPC computation per iteration of different self-collision avoidance strategies against the one without collision avoidance. The final adopted self-collision avoidance method increases only about 22% of the computational time. For environment collision avoidance, our final method only increases about 12% of the computational time compared to the one without collision avoidance. The hardware result exhibits the crucial role that self-collision avoidance plays in dynamic maneuvers where locomotion and manipulation are changing drastically. Dynamic manipulation, like object throwing, is also carried out safely on the hardware without collision. The throwing behavior can further be enhanced by dynamic gates, but still manage to avoid self-collision in the meantime. Moreover, the framework is capable of avoiding both static and dynamic obstacles with coordination between the arm and the body. Opening and passing a heavy resistive door without colliding with the door frame further exemplifies a real-world application of our framework. Thank you for your attention.